So what do we do with this? Our problem here is we're sort of given the opposite problem from what we had before. We're given a discrete time signal, and now we need to convert it. We're given a discrete time signal. Now we need to convert it into a continuous time signal. And there's no way to convert it into a single continuous time signal if there's aliasing. We saw that in the first problem where we had a whole bunch of different frequencies in continuous time, and all with aliasing converted down to the same signal. But if there's no aliasing, it converts down into a single system, into a single signal that's unambiguous. And the way to do that is to start off with the only equation we know to convert back and forth, which is y of n in discrete time is equal to y of t in continuous time, where you set your t equal to n t sub s. Now we want to go in the opposite direction, right? So we have this t equals, this little t equals n t sub s, and we need to solve it for n since we're going the opposite direction. So that's going to be n is equal to t over t sub s. So on with that, let's now say y of any t has got to be equal to, and this is in our continuous time, is equal to y of, in our discrete time, n, where n is equal to t over t sub s. And let's just compare, how does that, let's put in our t sub s. So if here our sampling frequency is 7 hertz, then our time sample must be 1 over 7. And remember what this is saying is that there'll be 7 samples every second. So therefore, every second, there will be 1/7. Every sample will be 1/7 of a second long. So that gives us, let's see, we've got 2 cosine. And what this means is every time we see an n up here, we replace it with t over t sub s. So 1/2 pi, and then our n goes to t over t sub s, which is 1 over 7. So that would be 2 cosine of pi over 2 times 7 t. And that's our answer. And of course, if you wanted to see what it could have been if it was aliased, you could modify this guy by adding or subtracting multiples of 2 pi and maybe flipping signs like we did in the last problem to see other possible continuous time signals that it could have been equal to. Questions about that one?
Or is it correct to say that there's sort of an infinite number of continuous time signals?
That's right.
That are equivalent to that discrete time signal?
That's right. That's right. There's only one continuous time signal that's equivalent to that discrete time signal if there's no aliasing, but if there is aliasing, there is an infinite number. That's right. Because we could have just as well, to this signal, we could have just as well added 3,644 n pi to it, and we'd end up with the exact same discrete time signal. But if you then did this work with adding over here 3,644 n pi, you'd get a very different continuous time frequency.